So in this lesson, we're going to look at how we can extend the use of integration from just finding areas into finding volumes. So let's start with an area. So the area in yellow here is under the curve y equals x squared plus 3 for x values between 0 and 5. But if we take this area and we rotate it or revolve it 360 degrees around the x-axis, it's going to create a solid shape. To help you visualize a little, that solid is going to look sort of like this. A little more symmetrical than I've drawn it, but still something like that, kind of like maybe a lampshade on its side. So something that is rotationally symmetric, and we can find its volume. Now, in order to do that, we're going to kind of visualize this thing being cut into slices. So if I imagine a slice of this, it's not perfectly going to be a cylinder, but the thinner the slices are, the closer it will be to a cylinder. Essentially, very skinny discs. And a disc, because it's not two-dimensional, actually is cylindrical. So I've got these very skinny discs, and this volume is made up of infinitely many of them. So each of these discs is basically, like I said, a cylinder. It's got a radius that is going to be equal to the y value of the function. So if I consider these slices on my original area, so a little slice like this, the height of that slice is going to represent the radius of the circle once I rotate it. So that radius is going to be f of x, or in this case, the x squared plus 3. The width of this is going to be delta x, because we want the width to be getting infinitesimally small so that we can add infinitely many of these together. So now think of how I would find the volume of the cylinder. The volume of this cylinder is going to be the area of the circle, so pi r squared, but pi r squared is pi times f of x squared, and then times the height of the cylinder, which in this case is the width of the disk. So that's delta x. Since we want infinitely many of these added together and we want them to be infinitesimally thin, this total volume, so this is the volume of the cylinder, the total volume of this shape is going to be an integral. So infinitely many of these things between 0 and 5 of pi times this function, and remember the y value of this function was calculated as x squared plus 3. So we have x squared plus 3 squared, because it's a radius, times delta x, but as delta x gets infinitesimally small, that is dx. So I can tidy this up a little bit before I integrate. I'm going to pull the pi out front because it's just a real coefficient. And I am actually going to square that binomial because that's going to make integrating it a little bit easier. So I have x to the power of 4 plus 6x squared plus 9 dx, which means that when I integrate this, the volume is pi times x to the power of 5 over 5 plus 6x squared cubed over 3, so that's just going to be 2x cubed, plus 9x evaluated between 0 and 5. So then when I want to evaluate this, I have to substitute in 5. So 5 to the power of 5 divided by 5 is just 5 to the power of 4, which is 625, plus 2 times 125, so 250, plus 9 times 5, which is 45, minus, when I substitute 0 in here, I'm just going to get 0. When we add all these terms up, we get 720, but remember that it is 720 pi. So the exact value of this volume is 720 pi. If you wanted to give an approximate value, you could say it's about 2,262-ish units squared.